It also evolves to the electrons and positrons. So now the neutrinos, because whereas before we were talking about Thomson scattering, the low energy limit of Compton scattering or electromagnetic interaction, we also have something else going on during this part of the story, which is electron-positrons annihilating to neutrino and anti-neutrino. So this is a weak interaction. So remember, for the weak interaction, we expect that the cross-section, well, we know the cross-section is going to go like gf squared e squared, or gf squared t squared, or as we wrote it, we just did the calculation earlier, as some beta squared, or beta squared t squared over mw to the fourth, where mw is the mass of the W boson. And our beta, 1/30th, and mass of W, we can just use 100 GeV for the purposes of our approximation. So we're now well below the 100 GeV limit, so this is the appropriate cross-section formula to use for the electron-weak interactions. And what we said is, in this case, we asked the question, what conditions are we in thermal equilibrium? And that reduced, in this case, to this condition. And if you plug this in with all the proper coefficients, this turns out to imply T less than around 2 MeV is when this interaction falls out of equilibrium. So now we are having a deviation from adiabaticity. So what's assumed about the neutrinos? So we'll go back to our diagram over here, which had temperature going this way, okay, and time going this way. Well, once again, think about this period of around about the mass of the electrons. When we went to high enough temperatures, temperatures above 2 MeV, so we're somewhere over here, the photons and electrons were in equilibrium. That's what we set up there. But now also the electrons and the neutrinos were in equilibrium. So we expect that the temperature of the neutrinos and the temperature of the photons would be in equilibrium. So in our diagram over there, we first of all showed the photons. Okay. But now I'll also add over here the temperature of the neutrinos. Then what happened to the neutrinos is just this interaction fell out of equilibrium. And when it falls out of equilibrium, it's going to be the same story as we had for photons when we talk about photon decoupling. Above 2 MeV, they're going to be in thermal equilibrium with the electrons and photons. They're going to have a Boltzmann-like distribution, a black body-like distribution with a temperature which is equal to that of the photons. When this interaction falls out of equilibrium, now the neutrinos are free to free stream through the universe. All that's going to happen to them is that their energy is going to be redshifted. Now, neutrinos are very light mass particles, so you can treat them as, in this very high temperature limit, as massless. So that just means their energy density is going to be redshifted, or their effective temperature distribution is going to be redshifted. But they will be redshifting as if they had as the same. They will have their effective temperature in this decoupled distribution will be the same as if they were in thermal equilibrium, because black body redshifted looks like black body at a lower temperature. So their effective temperature, they'll look like they have a Boltzmann distribution, but with the same temperature as they would have had if they had remained in thermal equilibrium at that same initial, at this temperature. So here's our 2 MeV. Over here someplace is 2 MeV. Okay. But meanwhile, the photons, what happened to them? What happened to the photons is they were doing fine. They were tracking the story up to here until we got to a point around half an MeV, where now the electrons and positrons were forming photons, but the reverse process wasn't occurred, and their energy density got boosted by this factor of 11/8, by this factor of 11/4 to 1/3.
You said half an MeV?
Somewhere around a half an MeV, yes, that's the mass of electrons.
Oh yeah.
Okay, right. So now we're looking in more detail at what's happening to the electrons in this case. Okay, first they're decoupling from the neutrinos, step one. Neutrinos are simply their temperatures continue to redshift. Then next, they decay, they pump their energy, they annihilate, and over some interval of time, they pump their energy into photons, so that at later times, where the effective temperature of the photons is now greater than the effective temperature of the neutrinos. Yes?
Sorry, I'm still a bit confused about this pumping of energy, especially since...
It's just that so we have all this energy in photons and electrons, okay, where we would have said, because it's in thermal equilibrium, the energy of the photons goes like T, and because it's in thermal equilibrium with the electrons, goes like T to the fourth with some G factor. Okay, the G factor for the electrons.
Yeah.
Okay, and what's happened is that the forward process continues, but not the reverse process. So that energy density that was stored here, so if we were plotting the energy density of electrons at this point, they would also have an energy density. I didn't do an energy density, I did temperature here.
Yeah.
If I did the temperature of the electrons, they'd be tracking this process, and then what's going to happen is they're going to annihilate, and over a short period of time, around when the temperature falls below the mass of the electron, all their energy is going to be converted into photons.
And because that's a T to the fourth, that's a T cubed, just that way.
Yeah, right. So just essentially because they're annihilating. So whatever energy density they contain, which went like T gamma to the fourth, is now going to add to the energy density, entropy and energy density of the photons.
Don't they stop going back and temperature equals ME because the individual gammas produced then fall below the energy of the electron?
Yes, that's
so
right.
it's harder because
then it goes from
one gamma to one gamma collision to now you have to have lots of gammas smashing into each other to get enough energy.
Because it's getting diluted.
Yeah.
Right.
Its capability to do it dramatically drops once the gammas go below the mass of the electron in energy.
This kind of process repeats itself over and over again
Nice.
in cosmology. It also has a lot to do with the formation of the first nuclei and the formation of the first atoms. It has to do, often it's not that you're deviating from thermal equilibrium, but what's happening is you're producing particles of, say, heavier nuclei. But then the inverse processes, which are still, so we're still satisfied the adiabatic criteria, but because of the expansion of the universe, there's not enough energetic particles for the inverse to occur. This is the same way. This is the same process that repeats itself at nucleosynthesis and at the formation of the first atoms and decoupling. So that means if nothing else happens to this story, and nothing much else does happen to this story, what you expect to see in the universe today is a thermal distribution of photons and a thermal distribution of neutrons, where there would be this temperature difference. So unless something else happens, that would be the prediction for the theory. Which means that if you were, let's say, wanting to calculate the entropy contribution of the neutrinos to the universe, you have to use this relative to the photons. You have to include two factors. A factor of 7/8 because they're neutrinos and not photons, and a factor of 11/4 to 1/3 would have to be included because they're not the same temperature of the photons. So this is one of those cases that when I was writing the expression for G star, and I was saying how different components can have different temperatures. If we were interested in the light species in the universe, the radiation species in the universe, and we wanted to write down the expression for the energy density or the entropy, For the energy density, they each go like T to the fourth, but with two different